Good morning, everybody. So we're going to be talking about unit availability and mitigating the costs of failures, because failures do occur and will occur. So unit availability is paramount for multiple reasons. Many of you guys are coming from utilities, and you're there to make power for a purpose of grid reliability, generation revenues. If your unit's not online, you're not making money. Also, on the other side, not just revenues, but on fines. With strict and frequent planning of generation, an unplanned outage can result in hefty fines. And also for water conveyance purposes, downstream users, irrigation canals, rafters. We've seen plants with multiple levels of redundancy just to make sure that you're not leaving kayakers on rocks. So all of these lead to fines, lead to unit availability concerns. Now, why is this relevant now? There is a trend, as most of you know, towards modernizing controllers. And this can be SCADA systems, unit controllers, excitation systems, governors. I'll probably reference governors a little more because that's what I'm familiar with, but these principles will apply to all types of modernized control. So if you have a relay board and a pilot exciter and a mechanical governor and you're replacing it, there is no equivalent replacement to what you have right now. So engineering decisions are going to have to be made about what you're putting into place. This opens the door to not just moving from something that you know and are comfortable with, but into something that you're maybe not as familiar with and you're not sure how reliable it's going to be. Also, if you are familiar with modern digital controls, you know that this opens the door for the opportunity to make improvements in your reliability. I'm going to talk about a few definitions that we're going to talk about through our presentation. Some of you guys may have seen before, some of you may not. First one, mean time between failures. This is the average time between component failures. Anytime any component in your system fails, that's considered a failure. It may not mean that the entire system fails, so it's a measure of the reliability of your system. How often do you have to work on it? How often are you seeing problems? Mean time to repair. This is the average time required to repair a failed component. How maintainable is your system? Is it easy to fix? Do you have to call in the experts from the regional engineering offices just to get it back online, or can your local technicians take care of the problem? Mean time between forced outage. This is the most important one. This is the average time between a total system failure. This is the average time between a unit coming offline and not being able to generate for you, causing those fines. And this is a measure of availability of the system. This is what we're mostly going to be concerned with. The final one, barely doesn't really need to be on here, but cost. The total cost to design, procure, install, operate, and maintain the system throughout its life. Not just the upfront cost of the materials. And we're going to look at several different options for installing control systems, ranging from a fully simplex system where you have single inputs, single power sources, going into a single controller, driving a single set of outputs. A little more complex, maybe you have redundant sensors, redundant power supplies, redundant power sources, all still going into a single controller, which has a single set of outputs. And then finally, fully redundant control systems where you may have multiple sensors going into multiple controllers, which are comparing data or voting, and then sending control signals to maybe multiple outputs, which are in a passive configuration where you have a primary and a backup control system. And we'll talk about each of these, and then we'll talk a little bit about where they may be applicable. So, fully simplex equipment. This is as simple as it gets, hence simplex. You have the minimum number of components required to make up a system. If you have a power supply, you only have one power supply. If you have a pressure transducer, you only have one. These are the simplest and the cheapest to design, the cheapest to implement and maintain. So therefore, you'll see that with the minimum number of components required, you'll have the highest mean time between failures. That's good. You'll run the longest before you have a component failure. Because they're simple, you'll have the lowest mean time to repair. They're easy to work on, they're easy to understand. Your normal plant technicians can replace equipment. But they are the riskiest to operate because any single component failure can cause your entire system to come down. So So they do have the lowest mean time between forced outages of the three we're going to look at. But they have the lowest cost. They're simple. So, if you want to increase your availability more than a simplex system, it's the next logical step. You want to duplicate the components that are most likely to fail, and the components that are easiest to duplicate. And that's typically your input signals and your power sources. Your power sources, because as most of you know, power sources are the most likely to fail. Power supplies, fuses, breakers, and they are easiest to implement because with most redundant configurations, there's no logic involved at all, just monitoring. Inputs are a little more complicated, but not much. You can bring 2, 3, how many pressure transducer speed signals into your controller, have a high signal select or voting algorithm, choose a single best signal, and then the rest of your system remains unchanged. So your mean time between failure does rise because you have more components. So you will have more. If you have more components will fail more often. You'll have more failures just by probability. Your mean time to repair will go up a little bit. Not much because it's a simple integration. It's not that much harder to replace a power supply when you have one power supply as when you have two, though it may get a little more complicated. But your mean time between forced outages will definitely go up. And this is because you have increased availability from two sources. Obviously your redundancy. If one power supply fails, swap over to the other one. You keep running. But also increased availability from additional diagnostics. If you have two pressure transducers and they disagree, you know you have a problem. If you only had one and it was off or was miscalibrated, you might not know you have a problem. So there's a whole another level of diagnostics and information that you gain just from simple redundancy. Now, step past this is full-blown redundant control. And there's actually several layers here we're going to talk about. The simplest is redundancy of your controller's CPU only. Next level would be a full redundant controller, including CPU and I/O. And then finally, looking at your output device. These controllers, through the spectrum from the simplest to most advanced, will lower your mean time between failures. Again, same trend. More equipment, the higher probability that you're going to have a failure. It will raise your mean time to repair because your system's getting more complex. But it will also significantly raise your mean time between forced outages because you're striving towards that kind of ambiguous goal of no single point of failure. And your costs will be the highest, not just in equipment costs, but design costs, implementation costs, and maintain costs.